Okay, good morning. So we can continue on our discussion about the membrane preparation. I think we are talking about the phase separation these days, and you can make the porous membrane or non-porous membrane depending upon how you prepare your solution, polymer solution, and coagulate them into the solid state membrane by using phase separation processes. This is an example of the symmetric membrane preparation by sort of a highly defined, confined polymeric membranes. What you could do is that you could use non-conventional, high-tech lithographic technique to prepare the porous membrane, starting from your polymer solution. And this was published in a couple of years ago. And what they have done is that they put the mask and photosensitize them to make the porous membrane with a very defined pores, which is not the same as the track-etched membrane that you have seen. And the track-etched membrane has a very randomly oriented porous structure, whereas if you're using this high technique membrane preparation method, you can make a very nicely aligned membrane with a nice pores. So as you can see here, you have a very defined pore, and particularly on the surface of the membrane, and in the bulk of the membrane, it may not be the same as in the surface, but through this technique, you can make at least a very fine porous structure, at least on the surface of the membrane. You can take a look at in the literature with the 3D well-ordered honeycomb structure, and not only in this paper, but you can see many other applications in the literatures. However, it's not easy to scale up this membrane preparation method in a large scale, because there are many, although it will be possible to make a small size membrane, it's not easy to make a scaling up of these processes. Because the traditional and conventional preparation method is much more economical than this high-tech porous membrane preparation technique. We can make the symmetric membrane with the TIPS process, and this is an example of polypropylene hollow fiber with the similar structure from the top to the bottom, or surface to the bore structure or inside. Using the TIPS process, we will talk about in more detail about what are the TIPS, but you can make a symmetric structure in this case as well. The outer surface looks a little rough, but it may have a very small pore. But anyway, you can make a very symmetric structure. By using this phase inversion, we can make not only symmetric structure, but we can make asymmetric structure as well. Okay, we can make a symmetric structure. In other words, we have a very thin layer on the top and a porous structure on the bottom, and that's what we call the asymmetric structure. And we can make a hollow fiber, we can make a asymmetric flash membrane, and so on. Thickness of the skin is the selective layer. This is the separation determining the layer of the membrane, and it's very important. The presence of this skin is what we call the membrane. Otherwise, you can call it as a film. Okay, film and membrane is different because the film is a relatively thick layer of the polymeric structure, whereas a membrane consists of the selective layer, which can operate as a transport phenomena or properties. So skin layer is on top of the support, and combining this skin and support is what we call the membrane. So let's let's talk about in more detail about how we can make a symmetric real membrane, okay, by using phase inversion or phase separation. So by using the phase separation, phase inversion, we can make a symmetric membrane from the one polymer. Okay? So I think we have given an example of cellulose acetate, Loeb Sorirazan type of the integrally skinned membrane. That's what they can call as a phase inversion. We can make a composite membrane mimicking this asymmetric structure. We have a porous support. If you coat very thin layer made of second polymer, then combine it together is what we call the composite membrane. Then we have to prepare the two different layers. First layer is a porous support layer, and the second layer might be the very thin selective layer layer. Usually the thickness of the skin layer might be less than 1 micrometer, usually less than 0.1 micrometer. The thickness of the composite membrane in outer membrane is known to be about 0.2 micrometer, and the integrally skinned hollow fiber membrane, if it's used in enriching the nitrogen gas from air, is about 0.04 micrometer. Okay, 0.04 micrometer. In other words, 40 nanometer, and the 40 nanometer skin layer is usually very common in gas separation area, whereas about 200 nanometer is common in outer and water treatment areas. First of all, we can think of flashing membrane by using nips or dips. Okay, dips and nips is about the same. And what we have to do is we have to prepare the dope solution. Dope consists of polymer, solvent, and additives. Okay, solvent should be the good solvent. Okay, good solvent should have the similar solubility parameter between the polymer and the solvent. So solubility parameter difference should be minimum in the 2D solubility parameter approach. Whereas if you add the additive as the bad solvent or the poor solvent, then the solubility parameter might be different, and it might be the larger between the poor solvent and the polymer than the polymer and the good solvent. Additives may be ethylene glycol or the pore forming agent, if possible, pore forming agent, or it could be, it could be the viscosity enhancer. If you're concerned about the low viscosity for a selected solvent system. Okay, so additives may not be just one component, but depending upon the producer, depending upon the how you have to prepare the very well-defined hollow fiber or fresh or whatever, this should be selected. Okay. Anyway, we could have a polymer, solvent, and additives. Then you can make a dope solution. Dope solution is just simply a solution. Okay, just like this, the yellow liquids. Then the second process is to put those solution on top of the glass plate usually, or if you have a porous support, then coat your solution on top of the porous support. Usually when you prepare your membrane in the laboratory, what you have to do is to just cast the film, cast the solution on top of the glass plate, okay, and pour the solution first, and using the casting knife, usually the Ghana knife, with a spacer in between these two spacer. If you don't have any Ghana knife, then what you will do is that you first put the tape, masking tape, on top of the glass plate, okay, and make a little the space between the glass plate and the top of the tape, And for example, if you have a 1 millimeter in the thickness of your layer of the masking tape, and if you have a 20% polymer solution, then you expect to have 200 micrometer. In other words, 1/5 of your final thickness of a membrane from the cast solution thickness, right? So because rest of them will be evaporated anyway, the solvent will be evaporated anyway. So you can first estimate your expected thickness of your the film or membrane, whatever, by controlling those Ghana knife thickness or thickness of your tape, masking tapes, okay? By knowing the polymer solution concentration. Anyway, by moving your casting knife, the polymer solution will be spread evenly from right to the left, so that by evaporating the solvent, you can make a very thin layer, dense layer on top of the support layer or on top of your glass plate. If you're using the glass plate and just evaporate completely the solvent, then you make a very dense film. Okay? It's very difficult to make a thin, very thin, less than 1 micrometer thin layer of your freestanding film by using just a glass plate. Okay? But you can, by in the laboratory, using this casting method, it's difficult to make a very thin layer on top of the porous layer even by using this casting method. Okay? However, you can make a dense layer, whatever the thickness you might be, on top of the porous support. Porous support usually could be a microporous polysulfone, or could be the non-woven fabric. So you can use this non-woven as a support layer anyway. This is what we call membrane, and membrane structure is symmetric. Dense skin layer, particularly the very thin skin layer, is very important because this is a selective layer and a very important layer in the future. Using the same dope solution, you can make a hollow fiber. Okay, first of all, you prepare the dope solution and put it into the reservoir. Put it into the reservoir. Let's see, where is the reservoir here? Reservoir, and by moving this polymer solution. Excuse me, this is the ball for it. Where is the polymer solution? Okay, okay, this is the polymer solution here. Polymer solution tank or dope tank. You put the polymer solution here, and you put the non-solvent in here. What you will do is that you push those two solutions into this spinneret, which is made of several holes. We have 2 holes here. In other words, this gray layer is a metal layer, whereas this yellow or blue layer is a hole. So you have 2 holes, 1 hole and 2 holes. So the polymer solution is fed from the outside of your spinneret. So it's coming from here. So polymer solution, and inside or from the top to the bottom is fed the bore. Okay? So bore fluid, usually the water, or in some cases water with solvent, is fed from the top, and from the side you feed your polymer solution. And those polymer solution, along with your coagulation, the bore fluid, is coming down to the spinneret, to the coagulation bath. I'm sorry. So into this small diameter of the spinneret, usually the diameter from here to here is usually around several hundred micrometer for the gas separation membrane. If you're making the water separation membrane, then diameter might be a little larger, up to about 1 millimeter or about 1,000 micrometer. The smaller diameter of this spinneret, smaller. If you wanted to make it smaller, then then you need to intend to use this fiber at high pressure. Okay? The fiber, for example, if you're having a fiber here, so yellow layer is actually the final hollow fiber layer, whereas this ball fluid is a hollow layer. Okay, so the diameter, total diameter, outer diameter, and inner diameter is very important. Finally, if you're thinking of the fiber, okay, the outer diameter and inner diameter, by knowing these two diameter, the numbers, you can calculate the wall layer thickness. Wall layer thickness ratio is defined as the outer diameter minus the inner diameter divided by the outer diameter. So wall layer thickness in this case is very small, maybe less than 10%, and usually for high pressure gas separation membrane is about 50%. So 50% of your full outer diameter is filled with the solid structure, and in the case of those 50% wall thickness ratio, you can use that membrane as a high pressure gas separation, whereas this thin layer could be used as a low pressure. For example, microfiltration. You can apply this very small the pressure. The reason why the thicker wall thickness ratio is necessary for your high pressure application is that if you apply the pressure from the outside or from the inside, of course, high pressure will burst off your fiber at very high pressure, so that you need the resistance to those pressure by increasing your wall thickness ratio. Anyway, when the polymer solution is exit from this spinneret, okay, from the spinneret, this polymer solution was pressurized so that you have a high pressure here, whereas you have a low pressure at atmosphere pressure here, so that because of the residual stress applied on the polymer solution inside the spinneret, polymer solution will become swell. Okay, you have a swell, so it's more like a swollen, just exiting outside of those spinneret. Okay, and then it will comes like this, and because of the gravitational force, and the releasing your pressure from the high pressure to the low pressure, you have a die swell just outside of your spinneret, and it's coming down and will be much smaller. It could be the same diameter as your spinneret diameter, or maybe larger, depending upon your air gap. So the air gap is defined as the distance from the spinneret to the top of your coagulation, the bath. So this air gap is important. So air gap determines your the diameter, final diameter. For example, if your spinneret is very close to your coagulation bath, then your air gap is very small. That means that your polymer, your membrane will be formed even with the stress at the die swollen state. So your polymer, the fiber will be coagulated like this, okay? Instead of your releasing your stresses. So the air gap distance is controlling your diameter and wall thickness ratio and the skin layer even. Okay? Now, temperature of your polymer solution, the dope solution, temperature of your coagulation bath also is very important. The speed of your polymer solution, the fed into the spinneret, speed of your ball fluid is also important. So there are many factors. Temperature of your dope solution, speed of your fluid coming in, temperature of your bore, composition of your bore, Of course, composition of this the doped solution, air gap distance, temperature of your coagulation bath, composition of your coagulation bath, speed of your the take-up roll, about 9 to 10 variables, parameters control the morphology of your fibers formation. Right? So you should be, although it looks very simple, it's an art. Okay, they said it's an art. Okay? They say it's not a science in making this hollow fiber. So this is the example of hollow fiber. Although it's not a good it's not good hollow fiber anyway. You have if you enlarge this layer, then this is the skin layer. We call this is outside skin. This is inside skin, but this is the bore side or the bore free side, and this is the outer layer. You see the macro void. You see these large holes, macro void, whereas you do not see any macro void here. This layer is called a sponge-like layer, whereas this layer is a finger-like layer. Okay? So this is the combination of finger with a sponge, and you may see very thin skin layers here. We will see how we can make the finger or how we can make a sponge. If we turn our discussion to tips, okay, the tips uses the latent solvent. What you call is a latent solvent. Latent solvent means that it's not a good solvent at room temperature, but it could be potentially a solvent in the future, right? If you increase the temperature. Okay, so that's what we call the latent solvent, which is different from just the normal solvents. Okay? The polymer is dissolved in the latent solvent at the temperature close to its melting temperature. So this, if you wanted to use this TIPS process, your material should be crystalline material. You need to have a melting temperature. The polymer should have a melting temperature if you want to use a TIPS process. We cannot use every polymer in applying the TIPS to make hollow fibers. So this process is that the polymer is dissolved in latent solvent at the temperature close to its melting, close to its polymer melting temperature. You can cast the flashy film using these tips, or spin the hollow fiber So you have a polymer solution, but you have to increase your temperature above your melting temperature, close to your melting temperature of both of those two components. At that melting temperature, above the melting temperature, your polymer is in the liquid phase. So this is also, we call that as a dope solution. But the phase separation occurs by the temperature, right? So the temperature is a driving force to make make a polymer. So by cooling down your polymer from melt to perhaps room temperature or maybe a low temperature, then crystallization occurs. So your crystals will be formed during those spinning or casting. So final polymer membrane has much more crystalline phases. This is why if you make this hollow fiber or a flashy film or whatever by using these tips, you can make a strong membrane. Okay? In some applications, we need some strength, mechanical strength. Therefore, they have to make a tips. They have to use a tips process to make a membrane. Latent solvent is not the volatile solvent. so that it should be recovered or extracted. Okay. So this is an example of the flashing membrane with a sponge structure or nodular structure. This is the PVDF process, the hollow fiber. We can replace this hollow fiber, picture with our own. But anyway, I think they prepared this at the ITM. So when we describe the phase separation process, this is the summary. Now, we have to think about the thermodynamic factor and the kinetic factors. Okay? We have to know about the polymer, solvent, and non-solvent thermodynamic aspects, as well as the kinetic effects. How, I have shown you about 10 parameters, important parameters determining the morphology of your final polymer structure. But you see the speed of your the pressurizing your polymer solution means that speed means time, and it's related with the kinetic parameters. Whereas the composition, polymer solution, polymer solvent, non-solvent interaction might be explained by the thermodynamic aspect. So thermodynamic and kinetic factor is involved in the phase separation. It's quite difficult to control everything. However, the phenomenological description of this process is possible with the aid of your phase diagram, usually the ternary phase diagram, because you have a polymer, solvent, and non-solvents in many cases. So we have to understand this phase diagram, first of all, in order to understand better later on what's going on in this case, both in the TIPS process and the NIPS process. Nevertheless, the phase diagram is a thermodynamic description, so we have to think about the kinetic parameter anyway in the future. So, for example, this is the phase diagram of the TIPS process, and in the NIPS process, it looks like this. So the TIPS process, you see, this is the polymer concentration in the x-axis. So when you have a solvent and a polymer, so polymer concentration increases in this way from the left to right, whereas solvent concentration increases from right to left. And y-axis is the temperature. So when the temperature increases, you can have a liquid phase in some cases and the solid phase. So I told you that when you have your solvent and polymer, particularly this solvent is a latent solvent. So when you mix these two and increase the temperature close to your melting temperature, your polymer will be melt and should be in the liquid phase. Okay? So this is the phase. This white region is the liquid phase region. So you can make a solution, you can make a liquid phase at low polymer concentration very easily, whereas it's difficult to make a polymer solution at high polymer concentration regions. And you have, green region, and the red region, and the black region here. So when you start from your point A, this is the point where you have your polymer and the solvent, increase your temperature, so you reach in point A. And if you cool down your polymer solution, you face your polymer will be anyway. If you lower the temperature from T1 to T2, you put you can solidify the polymer solution to become membrane. So this is the point where you have a membrane here. Anyway, during those A to B pathway, you experience some unstable region from stable region, and this is the stable region, of course. This is a stable liquid phase, stable solid phase. You face some unstable regions. And finally, from this point B, you may have a B prime point and B double prime point, where B double prime point is a polymer rich phase, and this is polymer lean phase, less polymer phases. You have your some line here, red, the green outside of this green region and outside of this red region is called binodal point and spinodal point. Binodal point is the one that you first experience the precipitation or crystal. You start your crystallization from this point, and there are some regions of the solution. This is the area where the polymer solution is not a liquid phase or is not the solid phase. Okay? And thermodynamically, this is very unstable region, and we can describe this binodal region and spinodal region by using the thermodynamic term, which is the Gibbs free energy mixing. Okay? Now, Gibbs free energy mixing should be always negative, right? In order to be a good mixing or good membrane formations. This is the point. The spinodal point is the one that you connect this line as a second derivative of your Gibbs free energy mixing. Divided by the X2 or the polymer. Okay? If this spinodal point is expressed by this, and binodal point is the one that you connect with the precipitation region, where the Gibbs free energy mixing is always positive or negative in this case. So we call this as a metastable region, and this red region is called the unstable region, and the rest of them are stable regions. In the case of NIPS process, we have a polymer, solvent, and non-solvent. You look very similar to what we have seen in our TIPS process. We have a critical point here, which is the top of those, where the binodal and spinodal meets together, and you have unstable region, metastable region, and stable regions. So, for example, if I have an A point here, A point means I have a polymer, maybe about 30% of my polymer. I may have about 70% of my solvent, and I have 0% non-solvent. I did not put any solvent here at this point, but if I move A point to here, that means that I may have about maybe 5% non-solvent. Okay? So any point can be described by the composition of those three components. So I have a liquid phase here, and it may travel following this A to B line, and B point is the one that you can have a membrane. If you look at this B point, I have about maybe about 35% polymer, and I may have the non-solvent might be about 70% or something, and I have about let's see. I don't have any solvent here. I don't have any solvent. So all the solvent is replaced by the non-solvent at this point. So the A point, starting from A point, you can travel. Your polymer solution will travel following this line pathway, and finally you can reach the B point, where all the solvent will be removed and exchanged with the non-solvents. And non-solvent could be extracted or dried and make a membrane. The same as the TIPS process, we have a polymer rich phase and polymer lean phase here. Excuse me, this is the polymer lean phase. And we have a metastable and non-stable regions. So we will describe this, the TIPS process and NIPS process by using the thermodynamic terms anyway in the following slides. In determining those phase diagram is very important. So we can determine the phase diagram if you are using TIPS process. We need to determine the phase diagram if you are following your NIPS process. So I will show you how we can determine those cloud points. Usually, when you have a polymer and solvent here and making a polymer solution, you drop your solvent. When you drop the non-solvent, in a small quantity, nothing happened. Right? But after reaching a critical the quantity of the non-solvent, adding to this polymer solution, the stored polymer solution, you start to see some precipitation points. Okay? Precipitation points. So the starting point could be recorded as well as the final precipitation points, and it's not easy. So the cloud point is the point where you reach your final precipitation occurs. So by knowing how many polymers were put into how many solvents, and you can determine also the quantity of your non-solvent reaching the cloud points. So this way you can determine the cloud point measurement. So for example, this is the example of some polymer and some solvent like a DMF and water, and you start from this point. Okay, this point means that you have a small amount of the water. Maybe water could be about few percent, like maybe 1% or 2% of your water into your dope solution. We have about 80, polymer content might be, let me see. So this is the water content. This is the, a little difficult. I think it's a little difficult to read. Can you point out the concentration of this point? Let me see, the water has about 1% or 2% here. This axis might be water.
And the polymer has about 9%.
Oh, yes. This is the polymer axis, and this is the solvent axis, right?
Yeah.
So polymer may have about 9%. Solvent might be about 91%, right? So you start from this point. What you do is that you add the water and get the cloud points. And the cloud points might be moved by changing your polymer concentration. If you have a second composition, third composition, stuff like that, you can you can make the all the connected structures. So this is the line where your bimodal distribution, the binodal points is. Okay, so when you determine your cloud points by changing your polymer concentration and then connect them, this is the binodal points. It's very difficult to measure the spinodal points, so you just determine the bimodal points in phase diagrams. After making these bimodal curves, you can start from you can make the if you go back. Okay, if you go back. So this way you can draw the bimodal points, and next point that you have to think about is that where you should start to make your membrane. Whether you start your membrane from here, this point, or here, will determine your final morphology of your polymers, membranes. Okay, so we have to think about those thermodynamic points, and what it is that usually you can make a macrovoid finger-like structure or sponge-like structure, or you can make a thin skin layer. Those are not be exactly determined by where your point is, But you have to think about your kinetic parameters to finally pinpointing finger or sponge-like structures. So in addition to the thermodynamic factor, we have to think about the kinetic factors in this case. We need to think about your macro void as well. Macro void was the one that looks like the fingers. Right? Macro void. When you form the macro void, usually the macro void starts to form, and finally it will propagate and grow into the larger ones. And this slide will show you how the macro void will be growing. It's difficult to see you in this case, but there is a dark black line, and this black line is the macro void. What it is that as when your polymer solution meets the non-solvent, you have some interface between non-solvent and solvent. And when you think about your interface, your polymer solution containing polymer and solvent was intruded by the non-solvent, so that in this case non-solvent and solvent might be and should be miscible, completely miscible. So non-solvent meets the polymer, and non-solvent is intruded into the solvent cage, and this is something like this. So this is the non-solvent, and this circle might be the non-solvent here. Now, in this case, the solvent should go into this non-solvent cage, and so that you're in this case you have the non-solvent will be intruded again and again, and as a function of time, this small cage will start to grow, and at final time from T1 to T2, you can have a growth of your macro void. That way you can form the macro voids. And this is the kinetic factor because this is really with the time. Okay? So you have a mass transfer from the front, and this is what they call the spinodal front of the growth. Macro void can be avoided by controlling many factors. First of all, you can reduce the film thickness so that the spinodal point should be very much faster. There is no time to grow because the thickness is very small. You don't have much polymer solution to the final structure. That way you can reduce the time to grow, or by adding the solvent in the coagulation bath, or by adding the additives into the casting solution. That way you can remove your macro void and form the nicely packed sponge-like structures. If we move to the two-component polymer cases, this is the diagram that you have already seen. So we can make a phase diagram similar to this one before you spin your hollow fiber or casting your solvent by using TIPS process. So we can theoretically explain what's going on into this phase diagram by exemplifying this TIPS process. Well, thermodynamic factor, for example, the Gibbs free energy mixing can be defined as delta T minus T delta S, and it should be always negative in order for your polymer solution to be mixed to form your polymer membrane. Okay? Now this is the difference, Gibbs free energy difference between the first phase and the second phase. So the Gibbs free energy mixing should be always negative. If we have So what about what about the enthalpy? Okay. We know the temperature. Temperature is just a Kelvin temperature, and S is an entropy. Entropy could be increased by perhaps a stirring. Okay, perhaps a stirring. Enthalpy. What about enthalpy between the polymer and your solvent? Okay. Enthalpy. If you think about the mixing between the polymer and the solvent, in order for the polymer and solvent to be mixed well, we have a polymer and polymer interaction, solvent and solvent interaction, and polymer and solvent interactions. When we think about our polymer solution stages in the liquid phase, polymers and solvent interaction is much larger than polymer-polymer interaction and the solvent-solvent interactions, right? In that case, polymer and solvent interaction is larger, then delta H should be negative. Right? If delta H is positive, then PP and SS interaction is much larger. Right? So that's the meaning of enthalpy changes between your polymer and the solvents. So for delta G to be negative, right? To be negative, in this case, delta H, where the delta H should be negative, right? Polymer and solvent interaction is negative. And T delta is always positive because T is much higher and you increase your entropy anyway. So T delta is a positive term. So you have negative second term. And the first term, of course, should be negative, right? So in that case, you mix your polymer into your good solvent. Okay, good solvent is the one that the polymer and solvent interaction is much larger, so that you have a negative delta H. Poor solvent is the one that polymer-polymer interaction and solvent-solvent interaction is much stronger than polymer and solvent interaction. So in that case, poor solvent has a delta H of positive. Right? If delta H is equal to 0, then means that you have equilibrium, equilibrium stages, like a precipitated stages. Right? So that's what it means by the delta G, negative delta G and positive delta S. So when we plot delta G of mixing with the polymer concentration, okay, X2 or mole fraction of your polymer, then in order for us to get the negative term, negative delta H, negative delta G means that your chemical potential from the first phase and the second phase is always negative. So in this region, you have a mixing. However, delta SM is always positive, and this is what we mean by this. And if you think about another thermodynamic aspect of a free energy mixing, is that we can have a derivative of this delta G. Okay, derivative, first derivative and second derivative. First derivative when the first derivative is equal to 0 and the second derivative is equal to 0. This is the point where we talk about the spin order points. And the first derivative of the mixing could be understood as well. So when we have a mixture, the maximum point where delta G of mixing is positive, this region is always regarded as unstable region because we do not have any the mixing stages. Well, delta G of mixing, if it's negative, then this is the region where we have positive cases. Now, we can find the first derivative and second derivatives, and this is the region where we have a second derivative is equal to 0, these two regions. So in between these two, we have quite unstable regions in between these spin order points. Binodal points is determined right in here, and this point. And in between this binodal and spinodal, this is the region where our polymer solution is not stable, is not unstable, is what we call the metastable regions. And this is the point where our second derivative, this is the first derivative, this is the second derivative point, 2 points, is regarded as the point where we have this one. So the first derivative point is regarded as a binodal point. Second derivative point where this is equal to 0 is called the spinodal point. Okay? If we draw the first derivative and second derivative as a function of the mole fraction of the second component, x2, the first derivative, when you have the first derivative is 0, point 0 here, 2 point is called the binodal point. Second derivative is equal to 0 point is called the spinodal point. Right? So when when delta G is equal to negative and second derivative is equal to positive, when we have first derivative is equal to delta G is always the negative, and delta G of mixing is positive, which is this region is regarded as a stable region, whereas the delta G is equal to positive and second derivative is always negative, where this point is called the unstable region. It's very similar to what we can describe in the TIPS process, so temperature-induced phase separation, where this is the critical point, the point where the binodal and spinodal meets together, and is the same. You have stable region coming down to the binodal point, spinodal point, where you pass your metastable region, and pass also the unstable region, where the second derivative is always positive and delta G is negative and delta G is positive, and you meet with the B point where everything comes down to make the membrane. In making this the membrane processes, you always, because this is the TIPS process, you start to have your crystal initiation or nucleation and then grow, so that there are some other kinetic factors other than this thermodynamic factor that we have just described. So nuclei, size of this nuclei could be influencing the size of your polymer and mechanical strength and everything. So the polymer solution and crystal size depended upon the rate of your nuclei. This is the typical and practical phase diagram in the case of making your polymer membrane. This is an example of your PVDF, polyvinylidene fluoride polymer concentration from 0 to about, let's say, 60%, and y-axis is the temperature. Now, we can have the point where you form the crystals. So by changing the polymer concentration in the latent solvent, in this case a DOP, diactive phthalate. Diactive phthalate is regarded as a plasticizer in making your PVC, polyvinyl chloride, films and pipes. This DOP is, however, very toxic and carcinogenic, and it's banned in many parts of the world. But still, the DOP could be used in many countries as well, in making membranes and films. PVDF is in the solid state in the room temperature, of course. the melting temperature is above 200 and I think it's about 220 degrees C. The DOP, by adding this, DOP is a room temperature, but it could be melt. It could be in the liquid phase above 200 degrees C. So temperature, if you increase the temperature to 200 degrees C or above, you can melt those PVC and make a dope solution. Okay, and if you cool down your temperature, then you can find the crystallization temperature by changing your polymer concentrations. By adding your polymer and cool down your temperature, you can measure these points. This is the point where you have. And this is the cloud point where you form your clouds. You can precipitate your polymer by adding some of those the temperatures. So when your cloud point and crystal temperature meets, this point is called the monotactic point. I think we have described here. Monotactic point or monotactic composition, so that the monotactic the point is important because it could separate the liquid to solid phases. And in the literature, you can find many of this type of your the phase diagrams, where when you have cloud points and crystal points meet together. This is the monotactic points, monotactic composition, and above this monotactic composition, you have a liquid phase. We have a solid phase or liquid phase here. So you can pass this liquid to solid phase separation from by using this ETCFE polymer. This is one of the polymer produced by the Solvay company. Typically, you can make a sponge-like structure, not the macrovoid, using this TIPS process. But the temperature and of course the polymer concentration is important. ETCFE polymer has many fluorine components in the backbone of your hydrocarbons, and so that it's very expensive, difficult to make, but could be useful in lubricating the applications. And if you need a hydrophobic layer, that's the one that you can make use of this polymer. You can typically make this sponge-like structure or nodular structure using this TIPS process. This is very typical of your crystallization. And this is the typical example of the TIPS process using the Solef 6010. 6010 is a typical grade of Solvay PVDF polymer, and they have various types of PVDF ranging from 300,000 molecular weight up to about 700,000 molecular weight, and they have different names. 6010 means that this is the first mode product. They may have a 6015, 6020, 6030, 6040, stuff like that. And the high number, the high number means that you have increased the number of your molecular weight. And using this several grades of PVDF, you can make a typical PVDF hollow fiber, the membrane with the porosities. You can make a hollow fiber. I will just show you the recent results from the laboratory using PVDF 6010 with a Polar Clean. Polar Clean. I will show you why we are using Polar Clean in the next slide. But this is the typical process of making the hollow fiber. You can have a dope solution. You can have a dope solution, so you don't need any. You have a dope solution containing polymer and latent solvent. Latent solvent, here in this case, is not DOP, but could be but polacrene. Okay? Polacrene is much more environmentally friendly, and it's much more healthier than DOP, and so that's why we are using this polacrene. And if we use polacrene here, we mix this together and increase the temperature to above maybe 180 degrees C, and we prepare the diluents. Diluents could be water or could be polacrene. So this is regarded as the buffering. Okay? And you inject these two into the spinneret and push them into the coagulation bath, and by putting this polymer solution into a coagulation bath, you can make a stretchable. You can stretch them to make a much more strengthened fiber or strong fibers, and make hollow fibers. This is the typical the graph of the the crowd point and crystal point and gel fraction temperatures, and the point where these two meet is called the monotactic point. So above these monotactic points, it's possible to make the strong gelled the fiber membranes. Polacrene has a chemical structure something like this. We have a methoxy group. This is sort of ester, and you have acetamide, but you may have some kind of branched C4 in between these carbonyls, and it's known as the water-soluble solvents. This is quite miscible with the water, and it's known to be environmentally friendly. Now, if you use the DOP or as a latent solvent, I told you that this is very toxic. Right? During the PVDF manufacturing process, membrane manufacturing process, you have the DOP, which is floating around at high temperature, and by removing those DOP in the coagulation bath, it's not easy, so that you have to have a recovery system, and if you do not recover it completely, then it will be spilled off, and it contaminates your environment. And of course, the hazardous, the vapors at high temperature is very toxic. So as you know, this is carcinogen. And many countries, particularly in Europe, use of those DOP and even NMP at high temperature is banned in manufacturing those PVDF membrane processes. So they wanted to replace this solvent with an environmentally friendly solvent. That's what they call a green solvent. So this is all green color. It's made of the company called Rhodia. The company called Rhodia was formerly a Rompolan from the French company, but it was sold to Rhodia, and the Rhodia is right now the division of Solvay. So Solvay owns everything, and they use this kind of a water-soluble green solvent in the let's see, I think it's non-flammable. It could be used in agricultural activities. I don't know what happened, but I think they mix this water-soluble polacrene with some sort of pesticide and dilute them into cultivating the agricultural products. It's non-flammable. Toxicological and ecotoxicological profiles are quite excellent. I'll show you some of the data. And Hansen's parameter to solvents are quite similar to NMP and so on. So this is the the property and guidelines. I can show you the. I think you do not know much of those, but and I don't know much about this OECD, some numbers, but I can show you that, for example, acute oral toxicity in the rat is about higher than 2,000 milligrams per kilogram, meaning that usually the toxicity test is done by this type of test, and the rat, the small mouse, is one of the animal that could be tested, and they eat the these the rhodia or whatever, the polacrene or whatever the material, and when they have any non-toxic toxic environment, then you have a high number. Okay? The small number and high number means that if you have a high number of this value, that means that this material is non-toxic, less toxic than highly toxic material, which has a very small number in this case. This milligram is 2,000 milligram of this the polacrene in the kilogram of the rat. So this was converted into the 2,000 milligram of the polacrene in the kilogram of your rat. So you first measure the weight of your rat, and dose those polacrene to the rat, and see what happened, okay, in the rat systems. And if the rat died or may have acute oral the responses, then that's regarded as a toxicity, and you have a pretty okay in this number. And skin irritation test in vivo, there is no irritation. And let me see. Yeah. So I think they said all of this says that it's environmentally okay. And from the Solvay the brochure, I just wanted to advertise myself, advertise our laboratory here. Hanyang University uses this green solvent to manufacture PVDF membrane by TIPS technology from Hanyang, and they give two sites or three sites, in fact, in the world. The University of Connecticut, Professor Mekochan uses this polacrene in the membrane formation mechanism for FO application, for the osmosis. ITMCNL, Professor Drioli uses the TIPS technology to make an ECTFE membrane for membrane distillation application. And Nanopore FP7 project was funded anyway in this case. So we have conducted the PVDF membrane using this green solvent for the last 3 years, and we are in the 4th year, in the middle of the 4th years, and Dr. Kim and Juntae and Seogyung are working on this project. So I would just like to introduce you very briefly about using this green solvent to make a PVDF using the TIPS process next time. Okay, so I show you some of these, and so on Friday we will talk about and continue discussing about this TIPS process using this PVDF, which was made in the 10th floor. Any questions or comments? Very clear. Okay, thank you, and hope to see you on Friday.